Good afternoon and welcome to today's Machine Design webinar. Our topic today is When Precision Matters, a deep dive into air-bearing motion systems, sponsored by PI. I'm Bob Vavra with Endeavor's Design and Engineering Group. Let's talk about how you can participate in today's presentation. If you have any technical difficulties during our session, simply type your issue into the Ask a Question box and a member of our team will assist you. You can also click on the question mark Help button in the upper right corner of your screen. We also welcome your questions during our event today, and we'll get to as many of those as we can during the Q&A session that follows the main presentation, so feel free to send in your question at any time. To do so, simply type your question into the Ask a Question box and click the Send button. Also, please be aware that today's session is being recorded and will be available on the Machine Design website within the next week. You'll be notified by email when the archive is available. So let's meet our speaker for today. Nikta Jalayer holds master's degrees in electrical engineering and biomedical engineering. She has a decade of experience in the motion industry and has played a pivotal role in driving the development of precision motion and automation technologies across various fields of application. So Nikta, thanks for your time today. We're looking forward to today's presentation.
Fellow enthusiasts of machine design, my name is Nikta Jalayer and I am the Director of Business Development here at PI USA for their performance automation products. I'm truly delighted to welcome you to today's webinar, where we embark on a journey into a world of engineering elegance with submicron level precisions. Our main focus will be precision air bearing solutions, their principles, and the applications and markets they can best serve. Let's start with a brief introduction to Physik Instrumenta, PI. Physik Instrumenta, often referred to as PI, is a globally recognized leader in precision motion and positioning technology. With a very rich history spanning over 5 decades, 9 cutting-edge production facilities operating across 3 continents, and over 1,500 employees worldwide, PI and its partners are transforming the technological landscape. One of the major competencies at PI is the design and manufacturing of air-bearing solutions, which is the topic of this webinar. Let's explore that. To understand the essence of precision air-bearing stages, we must first grasp the fundamental concept of air bearings. Unlike traditional ball bearings or roller bearings that rely on rolling elements to reduce friction, air bearings offer a revolutionary approach by completely eliminating mechanical contact. They use compressed air to create a thin film of air cushion, which is typically around 5 micrometers to 15 micrometers in thickness. The cushion of air is sandwiched between 2 very flat surfaces, and it acts as a support. It helps guiding the movement of the motion platform and the application load. Air-bearing systems offer very high stiffness because the air film fully supports the bearing components. They show no static or dynamic friction even under the highest designed load capacities. And that means they have very high motion performance with nanometer level precision, and they can maintain this performance over the lifetime of the system, which is theoretically unlimited, because there's no wear or tear associated with these systems due to the frictionless design of them. Let's explore the critical considerations and innovations that go into crafting the structural design of air bearings. There are 2 primary methods to feed the pressurized air to the bearing gap. One approach is the use of orifices, which are small holes. They typically have 100 micrometers to 400 millimeters of diameter, The holes can be drilled directly into the bearing, or alternatively, specialized jeweled nozzles can be either pressed in or glued to the bearing. Another method involves using of porous materials. In this approach, the air is fed through a porous medium to create the air cushion. Common materials used for this purpose can be carbon, bronze, or steel. The relative benefits of each approach are debatable. For example, orifices, they offer precise control over the flow rate, and that allows for accurate adjustments of bearing-to-bearing gaps. They are also very well suited for clean room applications, and they can handle very high input pressures. However, there is a risk of the orifices getting clogged if relatively large particles find their way into the air supply, and that can potentially disrupt the system's performance. Let's explore the advantages and disadvantages of porous media design. Porous media has a natural dampening effect which helps to reduce vibrations or oscillations in the system. I just want to emphasize that with an orifice design, you can achieve the same dampening effect, but it requires proper design of the orifice's diameters and sizes. Porous design also, it generates a more uniform pressure profile across the bearing surface. Again, this is one of the characteristics of a porous design, but it doesn't mean that you cannot achieve a uniform pressure profile using an orifice design. You can simply achieve that by properly designing the orifice's locations. The porous media also acts as a filter for the incoming air, which means cleaner air gets to the bearing gap. Now, what are perceived as disadvantages? One is cost and complexity of manufacturing porous design compared to orifice design, because they typically are constructed using various materials, which is unlike an orifice design where you can simply drill holes into the bearing. We also said that porous media acts like a filter, which was a good thing, but that means that over time, the porous media can become clogged, and cleaning a clogged porous bearing is more difficult compared to a clogged orifice-based design. When talking about air-bearing precision systems, it is essential to highlight the important role of the air quality and the air supply in performance and reliability of these systems. The lifetime of an air-bearing system is virtually unlimited, but this only happens under certain conditions. First, it is important to ensure that the bearing surfaces, they remain undamaged. And second, the air supply, it has to meet specific criteria. This includes the air to be clean, it has to be dry, and it has to be free from oil contaminants. Basically, it has to follow several ISO standards that are listed here. For proper operation of air bearings, the supply pressure is typically maintained at around 80 psi. This can change based on the stiffness, the load, and the dynamic requirements of an application. But again, as a rule of thumb, 80 psi is the typical supply pressure we recommend. In terms of air consumption, it's again, as a rule of thumb, around 28 liters per minute per axis of motion. Preloading is another critical step in achieving and maintaining the high levels of stability and reliability required with these systems. Preloading is employed to fine-tune the performance of air-bearing systems. In order to maximize the stiffness of the air bearing and help maintain constant air gap, it is typical to preload your air bearings. Now let's explore some methods used to preload these systems. The simplest method is weight. Using a weight much heavier than the expected variation in the loading of the bearing preloads the air bearing system, and it ensures that it rides on a smaller and much more stiffer air gap, and it will be prone to height variations. However, it comes with the trade-off of increasing the moving mass, which means you're reducing dynamics. It might not be a problem for a lot of applications, but it is for sure a big problem for a lot of others. The second method is using a vacuum preload. In this approach, a vacuum is used to apply a preloading force to the air bearing instead of using the added mass. For this, you will need to provide an area of the bearing surface to apply the vacuum, and you will need a vacuum source. Because vacuum is limited to around -14 psi, and typically air bearing pressures are around like 80 psi as we mentioned, the net effect is still a lifting of the bearing even when the bearing and vacuum areas are exactly the same sizes. The third method of preloading is a magnetic preloading. Magnetic attraction between a magnet on the moving platform and a magnetic material on the stationary part of the motion system helps to add the additional stiffness. This configuration, it works very well for linear bearings, and it can be very cost effective. However, because many air bearings are made from non-magnetic materials, it requires adding other materials to the bearing, such as iron, and it might be a problem for some applications. The final method is opposing air bearing preload. This method uses, as the name says, opposing air bearings to preload each other. It provides twice the stiffness of a single air bearing, although the load capacity is reduced by almost half. Again, good for some applications, but not very good for others. Explore the material the air bearing systems are made of, as well as their structures. One of the most common materials for manufacturing air bearing systems is a hard coat airframe aluminum alloy. A hard coat typically implies that the aluminum surface has undergone a treatment process to make it exceptionally durable and resistant to wear and corrosion. The coating enhances the robustness of the material and makes it ideal for demanding environments. Airframe suggests that the material being used is an aluminum alloy specifically designed for use in aircrafts or aerospace applications. These alloys are chosen for their lightweight and high strength properties, making them suitable to achieve the highest dynamics possible. Precision milling and grinding of air bearing surfaces is a critical process in the manufacturing and maintenance of precision equipment that relies on air bearings. This helps to remove any imperfections in the structures, and it results in a smooth and defect-free surface to be used in air bearing systems. As mentioned previously, it is critical to maintain 5 to 15 micrometers of air gap in the air bearing system. Any imperfections in the structure or tolerances and dimensions of the parts used will have a direct consequence on the air gap. They might even potentially close the air gap. This means the bearing will no longer maintain its frictionless nature. It also means that the accuracy of the system will be compromised and precision and performance will be degraded. To achieve the desired level of accuracy, stability, and performance, the choice of motor technology is another critical aspect of the precision motion system design. Air bearings are usually paired with iron-less linear or torque motors for the system to deliver the highest precision at high dynamics while maintaining exceptional velocity regulations. And there are several reasons behind this choice. First and foremost, it is because iron-less linear or torque motors offer friction-free direct drive capabilities. This, in combination with frictionless air bearings, allows the system to have longer lifetime, handling more demanding duty cycles with very good dynamic response characteristics. Another reason is that these iron-less direct drive motors are engineered to eliminate any attraction forces between the motor and the magnets. And there is no cogging effect. And these motors can enable the positioning system to deliver smooth and very precise motion if they're paired with the correct guiding system. Resolution encoders, they provide the critical feedback needed to achieve micrometer or nanometer levels of accuracy and repeatability, and they are another fundamental part of the design of a precision motion system. Encoders are at the heart of any closed-loop servo system. They provide feedback to the controller to determine if the system reached the commanded position or not. So that means nanometer or sub-nanometer encoder resolution is essential for proper operation of a precision positioning system. But to choose the right version of an encoder, one must review the requirements of the application. For example, if an application should avoid homing or referencing to a position due to possibility of collision, then absolute encoders should be chosen because they can instantly report the exact position without needing a reference position. This is the exact opposite for incremental encoders. They require homing or referencing before they can report back the position. Other motion performance specs like repeatability and accuracy, they can dictate the resolution required for your feedback system, for example. Resolution is the smallest distance an encoder can measure. Encoder resolution is dependent on the signal period or pitch of the signal, electronic signal interpolation factor, and the electronic noise of the system. Let's set your expectations right. What kind of performance do you expect the system to deliver? To put this into perspective, imagine that you designed a motion system that flies over a thin film of air, so using air bearing guides. It is incorporating three-phase iron-less linear motors in combination with a 1 nanometer resolution encoder. If you think of this motion system as a jet, it will only deviate about 1 millimeter from its intended path when it is traveling over 1 kilometer at 475 meters per hour. So this is how accurate this system can be or will be. How would you know what to choose for your application? Air bearings or traditional mechanical bearings? Precision air bearing systems, they fly on a uniform thin film of air, and that cushion of air, due to the surface averaging effect, can compensate for micron level surface imperfections, which no matter what you do, there will be some micron level imperfections on the bearing surfaces of any system that you build. This means a motion system using the exact same motor encoder technologies will have higher accuracy, higher repeatability, and smoother motion if it runs on air compared to the exact same system running on mechanical bearings. This is shown here also on these metrology reports from two systems with similar travel ranges, featuring same resolution encoders and using the same motor technology. They're both using ironless linear motors. And you can clearly see the upper system running on air offers better accuracy and repeatability compared to the system on the bottom that runs on mechanical bearings. It is also obvious when you take a look at the runout errors. So the system on top running on air offers much lower pitch yaw errors, and it offers better straightness and flatness compared to the system on the bottom. Let's explore some of the applications that they can really benefit from the air bearing features. Precision motion systems play a vital role in semiconductor manufacturing applications, where nanometer level accuracy and repeatability, high speed and high throughput, and clean room compatibility are essential to different parts of the process. And these are all characteristics of a precision air-bearing motion system. Some examples of these applications are laser-assisted wafer slicing, wafer stealth dicing, wafer test and inspection, scanning and metrology, wafer etching, and lithography. Air bearings coupled with a direct drive motor technology deliver a frictionless motion system. This means that the driving system, meaning motor, controller, and drive, can directly convert electrical current into applied force. The lack of friction in the bearing means that there are no parasitic forces, and it is possible to directly control the force through the closed-loop servo with no need for an external force sensor. Air-bearing motion systems can control forces in micro and nanonewton levels. Examples of applications with force control requirements are polishing of flat or non-flat surfaces, micromachining, brake friction testing, assembly operations where a force must be applied during a weld or bond operation, touchscreen sensitivity testing, durability and life cycle testing of touch interfaces and push-button components, and so many others. With the increasing need to process, store, and convey more data at higher speeds every day, there is a growing demand for higher throughput, higher precision systems to manufacture silicon photonics devices. Since alignment is the lengthiest process in these applications, increasing throughput often means faster alignment. To meet this need, precision motion systems running on air bearings, they become very crucial to help and to achieve the levels of accuracy, dynamics, and durability these applications require. Optimized alignment applications, they involve very many small repetitive motions with high acceleration and jerk, which can limit operating life of mechanical bearing solutions. Featuring air bearings in combination with direct drive motor technology, the system will have unlimited lifetime and requires no maintenance. Different configurations, 3 degrees of freedom, 6 degrees of freedom, single-sided or double-sided systems can all be delivered to these types of applications and can all be manufactured using air-bearing motion solutions. As we navigate the ever-evolving landscape of precision motion technology, let's shift our focus towards the future and see what innovations and opportunities can be ahead of us. The future of precision air-bearing motion systems holds exciting possibilities. Here are some areas where we can expect future developments. Materials advancements to create structures with enhanced strength and reduced weight. For example, using carbon fiber composites or ceramics and other exotic metamaterials can help achieve better performances in these types of systems. The other area would be innovative manufacturing techniques like simulations and so forth to improve structural performance under dynamic loads. And we can also think about integration of active control elements within the structure to actively manage and optimize the performance of the motion platform. Another thing which is huge these days is leveraging data analytics and artificial intelligence to continuously monitor and analyze structural behavior, control loops, and control algorithms, and help to improve performance of the motion system. We can also think about advanced control algorithms that are tailored to specific environmental challenges so we can eliminate and address disturbances that may impact the performance of the motion system. As we look ahead, magnetic levitation stages are emerging as a groundbreaking technology. This is exactly where science fiction meets reality. To me, it is a technology that takes us one step closer to the futuristic worlds. Magnetically levitated motion platforms, as you can see, they are suspended in mid-air. There's no friction, no contact, and no limits to their precision. And as you can also see, there is a graph showing in position stability, and it is around 1.7 nanometers. These stages are highly dynamic. They are capable of very rapid and very precise movements. They are very well suited for use in vacuum and ultra vacuum environments. This makes them perfect for a lot of different scientific and industrial applications, like in many types of lithography applications. Magnetic levitation stages eliminate the need for complex cable management. They are simplifying the system design by eliminating the cables, and also there won't be any maintenance associated with the cables. There won't be any errors associated with cables dragging and so forth. They are also very well suited for applications like wafer handling and wafer transportation, where precision and cleanliness is very critical. In the end, I want to add that in the ever-advancing landscape of technology, the role of air-bearing systems will continue to grow, shaping the future of precision engineering and motion control. So as we step back into the world beyond this discussion, let's carry with us the knowledge that precision driven by the power of air continues to push the boundaries of what's possible. Thank you very much for your attention.
Well, that's all the time we have for today. If we didn't get to your question, we will be getting you some answers via email. So on behalf of Machine Design, I'd like to thank Nikta for an outstanding presentation today, PI for sponsoring today's event, and of course, thanks to all of you for joining us. Have a great rest of your day.